I'd like to welcome you all to the 2025, the first of the Canadian Association of Physicists speaker events, not the only one that's going to be held here at Western University, but one of a series of events held across the country. My name is Professor Paul Wiegert, and I'm a faculty member here in the Department of Physics and Astronomy at Western University, the University of Western Ontario, and it's my pleasure to introduce this talk and the speaker. So first we will start with a slide about CAP. So the Canadian Association of Physicists, for those of you who don't know it, is a national network, sort of the Canadian association for physicists across the country. They lobby government, granting agencies, international societies, and so forth. So it's sort of the top level of organization of physics here in Canada. They support events like the CAP Annual Congress, which we had here at Western last year. They also support national student physics conferences and the publication Physics in Canada. So if you're a student and you're wondering if CAP is for you, the answer is yes, it is. So there are ways for students, physics students, to be members of CAP. CAP funds international undergraduate student conferences, for example, as well as graduate student conferences. They have the famous CAP prize examination that you might know about. There are scholarships. The CAP Annual Congress has awards directed specifically at students, and there's a student advisory council where students studying physics can network and connect with other physicists across the country. So if you're a student and you're interested in getting associated with CAP, if you're an undergraduate, it's free during your bachelor's. If you're a graduate student, it's 1 year free followed by student rates, but it's a fantastic way to connect with the community that you're growing into. So, there was supposed to be a slide about land acknowledgement, so I was waiting for that to come up, but it looks like I have missed that one. So I will start with that now on my own recognizance here. So we acknowledge here that Western University is located on the traditional lands of the Anishinaabe, Haudenosaunee, Lunapiwak, and Chinanta nations, on lands connected with the London Township and Sombra Treaties of 1796 and the Dish with One Spoon Covenant Wampum. And in this, we respect the long-standing relationships that Indigenous nations have to this land, as they are its original caretakers. And on to introduce our speaker today, who has a very cool job, if you'll pardon the pun. Dr. Matt Stukel was born and raised in Ottawa and completed his undergraduate degree at Carleton University in applied physics. He then worked at Triumph as a radiation effects modeling research assistant, and after about a year he decided to pursue a degree in higher learning and completed his graduate studies at Queen's University. During his doctorate he worked on the KDK potassium decay project, which performed the first measurement of a rare electron capture decay of potassium-40. He then served as a postdoc at the Grand Sasso Science Institute, where he participated in a project known as COSINUS. And now he is working at SNOLAB, working on the search for dark matter with some very cool detectors that he's going to tell you about now. So please join me in welcoming Dr. Matt Stukel.
Hopefully everybody can hear me. It's a real pleasure to be here. I want to thank CAP for organizing this and Western for being such a great host. And thank you guys all for coming, and I hope you enjoy this talk. So, the title makes a pretty bold claim. You know, I'm a stranger, I haven't met most of you. Coldest detectors in our universe. Just a show of hands, who kind of believes that right off the bat? Nobody? Some people, 20%? Okay, a few of you. Well, it'll basically be my job to kind of prove to you that we are really operating some of the coldest detectors. But what does it mean to be the coldest? Let's try to put that kind of into perspective. So So if you were to think about maybe the coldest place, some of you might think of Sudbury last week, which got to -30, which was pretty cold at SNOLAB. Some of you might know that Ottawa and Ulaanbaatar regularly compete for the coldest capital in the world. Ulaanbaatar has recorded a lowest temperature of about -60 degrees Celsius. Some of you might know that the coldest spot on our planet is at Vostok Station, I guess the coldest measured spot, at about -88 degrees Celsius. And the clever ones here are probably thinking, well, the coldest spot in our universe is probably space, at about -270 degrees Celsius. But I'm here to tell you that actually the coldest spot is back in Sudbury, in SNOLAB, 2 kilometers underground, where there's about a square meter that's cooled to -273 degrees Celsius. And that's kind of the outline of the talk today. I'm going to tell you, how do we get that cold? Why do we need to be that cold? And then detail some of the experiments that use that temperature and what they try to measure. So, coolness. Paul actually already took my cool pun, so I'm going to start not quite using that today. But our life is just filled with cryogenic technologies. You can see, if you look at this plot, your refrigeration of your beer, your food, things like that. Refrigeration of vaccines that need to be shipped to different places. Superconducting, maybe in your labs, you've done a bit of that. Liquid nitrogen ice cream, all these kind of things. Cryogenic is a big part of all of our lives. And in this talk, I'm really just going to focus on one kind of small area, and that's ultra-low temperatures and rare event phenomenology. And in this sort of subgroup, we use what's called cryogenic calorimeters. Now that word has an origin in Latin. Cryo means ultra cold, genic means producing, calor means heat, meter means measuring. So it's an ultra cold producing heat measuring device. That's the sort of basis of the technology we are going to use today. There's a fun little history. The first calorimeter was actually developed by Black, Lavoisier, and Laplace. It was 2 concentric copper cylinders. In the middle, they put a guinea pig, and then they surrounded him with a wall of ice. They basically wanted to measure how his breathing and how much heat he exerted. So they had a little bucket, and as the guinea pig breathed out, it melted the ice, and then they measured how much volume they got over time. In the paper that I read, they did not hurt the guinea pig at all. He was completely fine, which is really nice. But that's the sort of first recorded experiment that we have with an official calorimeter. The next big invention was by S.P. Langley, who invented the bolometer. The bolometer is a type of calorimeter, but instead of measuring the heat that goes into the device, it actually measures the flux, so the change in heat flux. And so he used it to measure some properties of the sun. In the 1930s and 1900s, they started to use calorimetry to measure radiation, but the biggest innovation for what we're going to talk about today came in the 1930s and 1950s. In the 1930s, they got the idea for the first ever cryogenic calorimeter, which was aided by the idea of a dilution refrigerator. That is the core piece of technology that we really use in our experiments, and I'll go into a lot of details about that. In the 1980s, the dilution refrigerator was applied to particle physics problems for the first time by Farini up at Gran Sasso. So here he tried to measure neutrinoless double beta decay. This is a picture of the Quarry experiment, and it uses tellurium oxide crystals that it cools down. So I mentioned the dilution refrigerator, and this is a picture of what one looks like. If you ever see like a popular magazine that talks about superconducting computers, you often see an image that looks like this. This has nothing to do with actually the qubits or that part. This is just the cooling unit. It's the fridge. In general, it's comprised of 2 parts. There's a pre-cooling unit and then the dilution unit. For the pre-cooling unit, there's sort of 2 principles. You can have a wet dilution fridge or a dry. They both have advantages and disadvantages. The wet fridge basically is a bath of liquid helium that was cooled sort of externally. You bring it in a dewar, you kind of fill it up. The benefit of this is you have no vibrations. The bad thing is that you're constantly burning off liquid helium. So it's about, I think it's $30 a liter these days. So, if you want to run a dark matter experiment, that's 3 years, that adds up quite quickly. So most fridges use what's called a pulse tube or a cryocooler. This is a self-contained unit that basically compresses and expands helium in order to get the pre-cooling. The pre-cooling only gets you to about 4 Kelvin, And at this point, the dilution unit takes over. To kind of show you the different stages, you'll hear a lot of terminologies on how people refer to dilution units. Some people call them cryostats, some people just call them fridges, but they all are basically made up of the same sort of 5 stages. There's the top 2 stages, which typically are the 60K and 4K stages, and this is what the pre-cooling unit's connected to. It goes to about 4 Kelvin, and then the bottom 2 stages you have the still, which is this little square piece right here. You have the cold plate, which is its main piece is the heat exchangers, which is these coils, and then you have the most important point, which is the mixing chamber, which is this cylindrical object right here. These 3 stages make up the so-called dilution unit. And if you look at the temperatures, you cover over 4 orders of magnitudes in about roughly 1.5 meters. So there's quite a lot of cooling that takes place. I'm going to try to speak to both sides. Having both TVs is a little confusing, but I am worried about tripping, so I'll be careful. So we have the pre-cooling. This gets us to about 2 to 3 Kelvin. Then we get to the dilution unit. The first thing we need to know is the physics that sort of makes the cooling possible. And basically a dilution unit takes advantage of the properties of helium. So naturally occurring helium comes in 2 isotopes, helium-3 and helium-4. Helium-3 has 2 protons and 1 neutron, and it kind of behaves along the line of Fermi statistics. Helium-4 has 2 protons and 2 neutrons and behaves like a boson. When you cool it to 0.8 degrees Kelvin, you get this phase separation. So basically, if you have a mix of these 2 isotopes together, they're in liquid form by this point. When you get to that temperature, you'll see that the helium-3 will separate into a concentrated phase, where there's about 100% helium-3, and a dilute phase, where there's only about 6%. And it's this phase separation that gives us our cooling power. How does it work? Well, this is kind of a schematic of that dilution fridge that that you saw earlier. Basically, the mix, which is pre-cooled, is dropped down into this mixing chamber here. We can get it to that 0.8 Kelvin just by kind of expansion and contraction in the injection line. And when it gets to that phase, it separates. So on the top, right here, this kind of part, we have our concentrated phase. And then on the bottom, we have our dilute phase, which goes all the way up to the still. Now, one of the unique things about helium-3 is that its vapor pressure is lower than helium-4, which means if we heat the still just a little bit, we can evaporate helium-3 before the helium-4. That helium-3 goes away, and then our dilute phase is left sort of wanting some helium-3. Well, it's going to get it by this concentrated phase right here. So what's going to happen is a helium-3 atom is going to jump between the phases. And when it does that jump, it's an endothermic process, which means it's going to take heat from the environment. A carefully designed mixing chamber can sort of utilize that to basically the heat is taken from the mixing chamber, which is connected to a plate, and then that plate becomes cool. And that's how you get your sort of microkelvin level of cooling. And this is what's really at play in all dilution fridges. One thing I forgot to mention is pulse tube-based dilution refrigerators have a really interesting sound. It's kind of like a sh, 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 and that's the rotary valve opening and closing for the pre-cooling. It's actually a really big relief to hear. When you go into your lab and you hear it, you know your experiment didn't shut down overnight. So I like to think of it as the heartbeat. But yeah, this is the main tool that we are going to use to solve some of physics' biggest questions. So we have our instrument. We have something that can cool it down. The next part of the experiment, we need 2 more things. We need a device where the physics takes place. This is typically some absorber, some material, some detector. And then we need basically a sensor that can read out that device. With these 3 things, the absorber, the sensor, and the refrigerator, we can solve quite a lot of problems in physics, or at least attempt to solve it. Of course, the 4th kind of hidden thing is the people involved. It is really challenging to run the fridge. There's a lot of issues that run up. Basically, keeping one fridge cool is a full-time job for one person. That's our cryogenic technician, Pablo, who's very, very good at that. So, our focus today is going to be on solving the dark matter issue. But I just wanted to kind of give a brief scattershot of all the other sort of physics cases for that sort of setup of a fridge, absorber, and a thermometer. So I mentioned the neutrino-less double beta decay. That's the Poirier experiment. It's currently being updated into what they call Cupid. These are all acronyms, and I'm not going to go through them all. But basically, it's a huge cryostat that has over 1,000 detectors on it, and they want to find neutrino-less double beta decay. The nucleus and ricochet projects are really cool. They took a cryostat with a detector, and they put it right beside a nuclear reactor. The idea is that this reactor is going to shoot off neutrinos, which will ricochet inside the detectors, and that'll be a signal. What they're looking for is coherent elastic neutrino-nucleon scattering, or SEVs. You also, at the end of the talk, will talk a bit about quantum computing. So like I mentioned, those fridges are often in the images you see for quantum computing, and all around the world, people are using them. These kind of detectors are also great at seeing supernova neutrinos. So when a supernova happens, 99% of the energy is neutrinos, and they interact in that sort of sevens way. But the main focus on us is going to be dark matter searches. I just wanted to bring attention to some other cryogenic dark matter searches, CREST, Cosinus, Spice, and Herald, part of the Tesseract project, that are also around, but I'm not going to talk about them here today. So the focus is on dark matter. We have our tool, but we kind of need to understand the problem a bit more. So right now I'm going to give a brief, very short overview of dark matter. So we don't know a lot about dark matter. You can see the little cartoons like what is dark matter, where is dark matter. That's in the forefront of every paper basically these days. We do know that it represents about 27% of the mass energy budget of our universe, with dark energy being the majority at 68, and then ordinary matter at about 65. So to kind of convince you that there is dark matter out there, I'm going to present sort of 3 cases where there's evidence for dark matter. And each one of them is going to be at a sort of different scale. So the first one is sort of the galactic scale evidence. This is the rotation curves of galaxies. So the first thought that there could be something wrong in the rotation of galaxies really was done by Fritz Zwicky back in the 1930s. But the idea wasn't popularized until the 1970s and Vera Rubin and Ken Ford's experiments. So the basic principle is that we expect the rotation of galaxy to kind of, or the speed of the rotation to kind of decrease as a 1/r squared law. So as we get farther away from the center, we expect it to slow down. So it should follow something like this. You can see that the outer is moving a lot slower than the inner. But when we actually made the observations, we saw that the speed was sort of uniform. You can see in the picture on the right there that the speed at the sort of edge of the galaxy is equal to the speed in the middle. And the only way for that to happen, if you look at that equation, well, g is a constant, we know what r is, so there has to be more mass in there. And we can basically look at a galaxy and we can make an estimate on how much mass based on the luminous matter. So if we can't see this extra mass, it becomes this dark matter. On a more cluster scale, we have gravitational lensing. So here's the idea that if an image is far away, and then there's something very dense in front of us, as light travels from that source, it'll bend around the dense object. And depending on our perspective, it could change how it looks. So it could smear it, you could see multiple. This is the Einstein cross, so I think it's looking at a quasar, and the gravitational lensing is making it appear like there's 4 of them. It's bending around. Sometimes the universe can smile at you. I actually kind of think it looks like it's mocking us a little bit, because we don't know what dark matter is, but my own personal take. But these are sort of examples where if you look at something in the distance and you can't see anything in between you, but you still see this smearing, you know that there's an additional mass there and it's interacting gravitationally. So that's the galactic, this is the kind of cluster level, and now we have the sort of universal scale. So I'm not going to get too much into cosmology, but basically this is a map of the cosmic microwave background. It's the idea that 300,000 years after the Big Bang, photons stopped interacting with the protons and neutrons and electrons. And when that happens, they went free out into the universe, and this is the last picture. It's a little confusing to understand, but the analogy that I have always liked is how do you measure the roughness of the ocean? So if you're standing in the Pacific and the waves are hitting you, you'd have a pretty good sense of how big the waves are. If you're in an airplane, maybe you could still see a few big waves, but it doesn't look as rough. If you're on the moon, there's almost no roughness. And that's really what the measurement is here. So replace the roughness of the ocean with the temperature variation, which is the blue and the yellow here, and then you replace the scale with this L measurement. And that's kind of what that plot gives you. So on the x-axis, this is the scale that you're looking at, the angular scale, and then on the y, you see the power. Now, there are a bunch of bumps that all mean something, but the important thing to take away is the red line. This is a fit of the model. In this case, the model is this lambda CDM. CDM stands for cold dark matter. And if you look at that, you're like, wow, that's a really good fit. And what it shows that the data is consistent with is this lambda CDM model, which has 6 parameters. One of those parameters is the percentage of dark matter, which is how we get that 26%. Another thing the model assumes is that it's cold. In this case, it means that dark matter is non-relativistic, so it's not fast-moving dark matter. It gives us a few other things. It can tell us the Hubble parameter. It gives us basically the matter constant as well. But in general, this is our sort of universal evidence for dark matter. So with those 3 levels of proof, we can get some sort of starting properties for dark matter. 1, we know it's weakly interacting. There is no light emitted by whatever this matter is. 2, we know it's massive. It interacts gravitationally. The only things we know that interact gravitationally have some sort of mass. So that's one thing. From the lambda CDM model, we know or we expect it to behave non-relativistically. And I didn't really talk about it being stable on a cosmological scale, but people can do these models of the universe, which kind of branches out into galactic clusters. And if they assume dark matter is real, you see that it's sort of stable. So those are the sort of 4 properties that we start with for our search. Unfortunately, that's a huge range to start looking. So this is over 70 orders of magnitude that dark matter's mass could be. It goes all the way from these macroscopic objects. These could be like black holes, planets that are huge that we just don't make any light. It could be stars that are too dim for our instruments to see, all the way down to the ultralight scalars where we talk about axions. So it's impossible for one person to really look for all of this. So in general, people sort of pick their favorite and try to look for that. Mine is right in the middle in this sort of particle region. One of the reasons this is kind of nice is based on the standard model, everything we know that has a mass is a particle. We know that the standard model doesn't explain dark matter yet, but it could be that the standard model is not complete and there are other particles out there. So it makes sense to kind of look in that region. You'll also hear people talk about what they call the WIMP miracle. It's the idea that if it's at this weak scale level, kind of where the blue outline is, that amount of dark matter will have the right relativities. So it's a coincidence that it solves 2 problems at the same time. So it's a good reason to start looking there. And that's what we do. But even when you get to that small of a range, there's still a gazillion different theories of dark matters. We have WIMPs, light WIMPs, WIMPless dark matter, MeV scale dark matter. I've heard people use the name WIMPzilla. It's still a huge range to look at. So, the best thing you can do is kind of just pick and go for it. The experiment I'm going to talk to you today kind of covers the purple, blue, and green interaction scales, so that sort of mass range, but it is entirely possible to look at others. Okay, so I hope I've convinced you that there is some dark matter out there. I hope I've convinced you that there's a big kind of area to search. But if we wanted to do the particle way, how are we going to go about it? Well, there's 3 main ways to sort of directly detect dark matter. It's through this production, indirect, and direct. Production is when you have 2 standard model particles that you kind of collide together. So this would be at the Large Hadron Collider, any other sort of collider. And the idea is that this collision will make dark matter that'll escape. You won't see the dark matter in your detectors. What you'll see is some missing energy. And if you find the right missing energy, you find the dark matter. Indirect detection is pretty cool because basically the dark matter collides together, not on the Earth, but maybe in space, and it makes standard model particles. In this case, it's usually very energetic neutrinos or something like that, and this is detected in our big telescopes. So like the Ice Cube experiment in the South Pole, P1, the Pacific Ocean Neutrino experiment that they're building off the coast of BC. Those are the kind of experiments that can look for indirect detection. For me, what I want to look for is direct detection. This is when we have our little detector, the dark matter enters it, it sort of recoils, shakes it a little, and then we measure that. So it's a real direct interaction. To kind of assume that that's valid, we start with the traditional physics thing of assuming a spherical cow. What that means is a very base assumption for dark matter. It's isothermal, which means it has a constant temperature across our galaxy. We exist in a sort of galactic halo of dark matter. That dark matter is moving at this Maxwell-Boltzmann velocity distribution, and we have a rough measurement of the density, which is 0.3 GeV centimeters cubed. Now, to put that into perspective, if the dark matter was a 60 GeV mass, and you had a 2-liter bottle of Coke, there would be about 10 dark matter particles on average in that 10-liter bottle of Coke. Now, one thing to keep in mind is that although the dark matter is moving in our galaxy, so are we. And the relative motion between us is about 220 kilometers per second. And what that equals to is about 20 million dark matter particles through your hand, or the average hand, per second. Now, that sounds like a lot, but remember the dark matter doesn't interact very often, so even though it's 20 millions per second, that flux is still really, really low, and it's very hard to find the right signal. If we did find a signal, this is how we kind of expect it to look like. So I talked about recoiling. You can see some of the other experiments, named Ricochet and things like that. And it's basically that first-year physics problem of elastic scattering. You have a billiard ball and another one. One is the dark matter. It comes in, hits your detector, which has a large nucleus, and it recoils. Now, when that recoil happens, there can be two sort of scenarios. If the dark matter is a lot bigger than your sort of detector, your detector particle is going to go flying. You can think about, a bowling ball maybe hitting a ping pong ball. That ping pong ball is going to go flying. If it's the other way around and the dark matter is small and your detector particle is big, you'll see very, very small amount of movement in your standard model detector. So that sort of gives us two streams to go look for the dark matter. The first one is we could go look for sort of heavier dark matter, or we could go look for the light dark matter. When we look for the heavier, we expect big signals, but when we have the big signals, we actually have less dark matter flux because the large particle takes up more of the density. When we look for the small dark matter, the goal is to kind of push your resolution or your threshold lower, but we don't see a lot of energy transfer, but we do get a bit higher with flux. Now, I've been talking about these recoiling, but you can't just take a picture or a video of the lattice moving, or at least not very easily. So we typically rely on these three channels as sort of a signal. So it's scintillation. So in this case, the dark matter recoils. It generates a bit of light that we pick up in one way or another. It could also be charge. So if it's a semiconductor, or maybe it's a gas, you could have a little charge moving through it. Or the one you can probably guess we're going to talk about a lot is the heat transfer. So when something moves, it'll provide a little bit of heat to your detector. Okay, so hopefully I've convinced you that there is evidence for dark matter. We're going to look in a specific place. So we're going to look for dark matter and talk a little bit about the sort of channels available. But the next question is, where do we look for dark matter? Well, we look at one of the places is where I work, which is SNOLAB. So SNOLAB is up in Sudbury. It's a mine. It's in a mine, and it's 2 kilometers underground. This is kind of the schematic of SNOLAB right here. You enter the lab right about here. This part right here is the old SNO experimental cavity. So SNOLAB wasn't originally an all-purpose lab. It was built for just one experiment, and that's the SNO experiment, which you can see down here. Some of you probably know it won the Nobel Prize in 2015 for discovering neutrino oscillation. That work it did kind of in the early 2000s, late 1990s. And once it, or before it got that, there was a development into the new lab, which you can see right here. We have a few different areas. We call this part the ladder lab. If you ever go underground, that's where you'll find me. I usually work in this area right here, beside my experiment. Right here we have the J drift. So here they have some dark matter experiments that use CCDs, so kind of like the cameras in your phone. And then we have two big experimental halls. This one, because of its shape, is called the Cube Hall. It has the deep dark matter experiment and another experiment called PICO, and then the cryo pit. The cryo pit doesn't have an experiment in it right now, but the hope is that it will host a 1-ton scale neutrino-less elevation decay. Yeah, so SNOLAB is on the traditional territory of the Robinson-Huron Treaty of 1850. Like I mentioned, it's 2 kilometers deep underground. But an additional fact is it's a Class 2000 clean room. I'll talk a bit about that later. It hosts numerous particle physics experiments. So it's in an active mine, and that mine is owned by Vale. And if you ever go to Sudbury, you actually see a lot of mines in that area. It's a big mining town. And this is a cool video that explains why it's such a cool mining town.
I'm before life on the Earth, in a world when Sudbury was south of the equator. An event took place that would change the course of mining history forever. This is a time before time. 1.85 billion years ago. It came from above, a 10-kilometer.
Oh, sorry, that was me.
That was you. Oh, sorry.
I'm not sure I turned up the volume.
It was too good of a video. I understand.
Well, this one's sorry.
I can turn it off on my laptop. Okay.
Sorry.
Yeah, no problem.
Time before life walked the Earth. In a world when Sudbury was south of the equator, an event took place that would change the course of mining history forever. This is a time before time. 1.85 billion years ago. It came from above, a 10-kilometer wide intergalactic rock, hurtling on a path of destruction toward our young planet. Life had yet to evolve legs, but even if it had, there was nowhere to run. The meteorite punched a hole in the Earth's crust, 30 kilometers deep. The destruction was absolute, but out of the burning pool of liquid planet, new rock formed, unlike the old. As the rock cooled, rich pockets of nickel and copper ore separated out into some of the richest mineral deposits in the world.
So if you ever go to Sudbury, there's a Museum of Science North where you can find that video. But it just goes to show that we've really been planning for these experiments for 1.8 billion years.
I'm before.
There we go. So the question you're probably wondering now is why do we go all the way underground? What's the benefit you get from putting a lab 2 kilometers? Well, the biggest one is the reduction in background. So on Earth, right now, kind of where we're standing, there's about, I think the number was 10 muons in your head every second. So they're just going in and you can't feel them. But these sensitive dark matter detectors definitely do feel them. And when you put it in a depth like SNOLAB, you get 1 muon in your head per day. So it's a really, really small amount. It's a huge reduction. There are many underground labs in the world. One of the more famous ones is the Grand Sasso. SNOLAB is the deepest, cleanest lab in the world. It is not quite the deepest. This is a log scale, so it's hard to tell. But the one in China is just a little bit deeper. It's not a clean lab, though. So that's the second sort of step that we take to reduce our background. So you can imagine the mine is very dirty, it's full of dust, and the mine dust is really bad because it's filled with uranium and thorium. These are radioactive isotopes, and when they decay, they leave really bad particles, specifically alphas, which make neutrons, and neutrons look a lot like dark matter. They have that same sort of recoiling structure to it. So everything that goes into SNOLAB is clean. We have a dedicated team of cleaners. We call it a Class 2000 clean room, and that just means that there's less than 2,000 particles that are bigger than 0.5 micrometers per diameter per cubic feet. Now, in addition to the cleanliness program, each experiment has its own sort of unique shielding. So there is still radioactivity coming from the components of the experiment, coming from the walls, the shotcrete that we use to paint everything. So you often see it as sort of an array of shielding. Usually it's water, lead, copper, and plastic to kind of get rid of everything else. The other thing that SNOLAB does is it screens all of the components that come in for its radioactive purity. So when they're building these detectors, they'll take a sample, send it to us for screening, we'll tell you how radioactive it is, which will then decide whether you use it or not. So it's a huge cleanliness effort, and it's really one of the most unique things about this lab. It's really, really clean. And to kind of give you the sense, I had another video here. So this is what it's like to kind of go into SNOLAB. And I'm going to talk over this one a bit. So right now they're in a cage. You take a mine shaft down, you'll see some light flash. Those are the different levels. Remember, you're going down about 2 kilometers. So you start dressed up in this mine gear, headlamp, all this protective stuff, and you're kind of squished in a little bit like sardines. So each cage can hold about 40 people in rows of 4 to 10 deep, and then there's 2 of them on top. This video was taken a while ago, but you now actually have to stand sort of face to face, so you're right in front of someone else. Once you get to the SNOLAB level, they call it 6,800. It's about a 1.5 kilometer walk, so it takes maybe 10 minutes just to reach the lab. It's a pretty even walk. It's like walking on a forest trail. Yeah, you can see there. They don't let us ride in the mine car, which is not great. And then once you get there, there's a boot washing station just to the left, so you have to clean all the dirt off before you even get inside. I'm just going to pause it. Hopefully I can do that. Sorry, it's going to have to go again. But what I wanted to say is that when you get to the lab itself, you are not allowed to enter in your mine gear. So we have a dedicated shower facility where you really have to wash yourself down, especially your hair. Hair is the largest surface area of your body, so it gets filled with mine dust. You can see these caps don't really block it out. So you spend about maybe 10 minutes showering before you can even enter the lab. When you enter the lab, you wear these special Tyvek suits. You'll see them walking in the, we call them the blues, in a second. Yeah, so this part we saw. It's also it's a 10-hour straight shift underground, so you have to bring your lunch. There's no Tim Hortons, unfortunately, underground. And then this is inside SNOLAB. So you can see already the big difference. It just feels, it looks cleaner. Those are the suits I was talking about. The shirts and underwear are also provided by SNOLAB and extra clean. This is the Snow Plus control room. That's the snow detector. You can see the little PMTs lighting up. This is the deep experiment when they were building it. This is the Q hall, so it kind of looks like this square if you could see it. This is the top of the deep neck. This is inside the deep water tank. So inside that sort of sphere, they have a whole bunch of liquid argon, and that's how they look for dark matter. Some Snow Plus neutrino results. This is the halo experiment, which is supposed to detect supernovas when the next one happens. This is where Pico 500 is going to go, also in the Q hall. And then that's an old, I think it's an old Cooper Pico detector. So you kind of get a sense of what SNOLAB is like. So we talked a little bit about the advantages. So now we'll have the ad break for SNOLAB. So they do pay me, so I have to tell you that we do hire undergrad students. Basically every semester we'll have about 12 to 15. The current closing date for applications is February 1st, so in a few days. So I won't be offended if you spend the rest of the presentation applying. But we also hire in the fall and the winter, and every level of undergrad, from first year to even after you've graduated 1 year. So it's a lot of fun. So if it looks like something you'd be interested in, that's a place to check it out. Okay, so we have our problem, which is dark matter. We have our location, which is SNOLAB. We have our tool, which is a dilution fridge. We have the perfect recipe now for an experiment. And that experiment is one of the ones that I work on, which is a super CDMS at SNOLAB. So this plot is, if you ever go to a lot of dark matter plots, you always see something like this shown. On the x-axis, you have the mass of the dark matter particle, and on the y-axis, you have its probability of interacting. And the way to read this plot is it's almost like a game of hide and seek. So these experiments, they draw what we call limits that go up like that, and they basically say that we have looked down to this point, and we have not found dark matter. If they were to find dark matter, it would look kind of like these contours right here that you can see. You can ask me about those ones later. But basically how it works is anything in green has been ruled out. Those are areas in the parameter space where experiments have already searched. And it's kind of broken up into two areas. You have this heavy sort of dark matter size, usually above 5 GeV. What's interesting is that cryogenic experiments used to be the dominant ones in that area. But as to go down on this plot, to search deeper, you need more and more exposure. And just by the nature of cryogenic technologies, it's not easier to build more and more together. And now these sort of noble liquid experiments have started to dominate. So like DEEP we talked about, xenon is another one. And they're the real drivers of the search in this area. Which means that the cryogenic experiments had to shift their focus. So instead of getting bigger and bigger targets, they wanted to get better and better resolution or threshold. So instead of going down, we went left. And this is the area that Super CDMS is going to target with its experimental search. The CDMS stands for Cryogenic Dark Matter Search. If you go into particle physics, you have to be good at acronyms, because we need to get better at them. Super is because it is a new, there already was a CDMS 1 and 2. Super was the upgrade. The first Super CDMS actually took place at the Stukel lab in the United States. And then this is technically, the full name is Super CDMS at SNOLAB, because it's the first experiment at SNOLAB. It's deeper and another upgrade. You'll see some particle physics experiments that when they go like upgrade again, they'll go hyper. So you've probably heard of hyper chemiocandidate. There was a super chemiocandidate and a chemiocandidate before that. It's a big collaboration. There's about 100 members, over 27 institutions all over the world. This was our last collaboration meeting up at SNOLAB. And I've kind of talked a little bit about this, so I'll go through it quickly. But this is our sort of target area where we want to look. This is the mass range we're aiming to really do our search in. So there's 1 EV to 1 DV. And what enables us to do the search is the interaction with dark matter with different parts of our detector. So the sort of heavier, sort of standard dark matter scattering is this middle drawing right here, where you can read it as the dark matter just scattering off the nucleus of our detector. The one to the right, it's off the electron, so that's typically a bit lower, maybe 1 keV to 1 MeV. And then we also have this dark photon that we can look for that really allows us to push down to the lower mass ranges. So what do our detectors look like? Well, they kind of look like that one up there. In reality, it's made out of silicon and germanium, and it really looks like a big hockey puck. It's about maybe this big, that thick, and it rests in these sort of copper boxes. There you can see an example of an ISIP. The reason we have 2 target masses is, if you remember, I had that scattering picture earlier. If the dark matter is lighter or heavier, you get a different amount of scattering. So it's beneficial to have the 2 silicon and germanium. Germanium is a lot heavier, silicon is a lot lighter, so they serve different purposes. Additionally, they are semiconductors, which means we can see charge. And that's really our 2 channels that Super CDMS focuses on, which is phonon, or the heat transferred to the detector, and the charge. The heat, the way it works is you have your you can imagine your slab of silicon or germanium here. You have the dark matter interact. It causes the lattice to recoil a bit. movement of the lattice is known as phonons. So these phonons, in this case athermals, will travel through our absorber and eventually get to an aluminum strip on the top. The reason we need to be so cold is that this aluminum strip needs to be superconducting. So when it's superconducting, there are these Cooper pairs on the inside. The phonons travel up, it breaks these Cooper pairs apart, and they become sort of quasi-particles. These quasi-particles move along the aluminum strip into this transition edge sensor. This is typically a thin filament of tungsten, and there's a little barrier here, and basically what happens is as these quasi-particles go into the tungsten, it heats up the tungsten just a little bit. And that heat is what we actually end up measuring. The full name for this, I can never remember it myself, is quasi-particle trap-assisted electrothermal feedback transition edge sensor. That's the name of the detector, but it's a bit of a mouthful. So that's one of our signals. The next one is the charge. So this picture right here you can see is an ISIP detector. It's one of the ones that can measure charge. And basically there are interleaved electrodes right here. When the dark matter interacts, it creates electrons. There's a slight potential across the semiconductor here, and these electrons induce a charge in these anodes that you can see right here. And that's the second signal. The benefit of measuring both the heat and the charge is just another form of background reduction. So what that means is if we have two signals, particles will interact in a different way. So for example, if we have a gamma ray interact in our detector, it'll make a large phonon signal and a large charge signal. If we have dark matter, it will only make a phonon signal and not make a charge signal. So you can see by having the two channels, we can discriminate whatever remainder background we have left in our detector. Now, I mentioned the last step was this transition edge sensor. It was that little piece of tungsten. And this is really the reason we need to get to millikelvin temperatures. So tungsten has two superconducting critical temperatures. One of them is very low. It's a little dependent on the purity of the tungsten itself. But basically, when something goes superconducting, it has no resistance anymore. What happens in this state, well, no resistance, you guys know. So what we do is we operate this tungsten in its transition state. So kind of right before it goes superconducting, so right in here. And what that does is basically a small change in temperature is a large change in resistance. And that's actually what our physical measurement is. So the sort of sequence of events is you have a deposition of energy, you have lattice vibrations, the phonons, they go through the aluminum, but they eventually change the temperature very slightly in the tungsten. When that happens, you get a large change in resistance over time, and that's the ultimate signal that you read out right here. And then from there, you can do your sort of standard analysis where the pulse height is correspondent to the energy. One of the big upgrades between SuperCDMS Sudan and SNOLAB is we've reduced our critical temperature down to about 40 millikelvin. The resolution of your detector, so this is kind of how thin the widths of your peaks are, where your threshold is going to be, scales as a function of the critical temperature Q. So even though it's only a reduction of 50 millikelvin, that's a huge decrease in resolution or increase depending on how you think about it. We're not the only experiment to use these transition edge sensors. CREST, Cosinus, which I mentioned, use it as well. They operate a little bit differently. They don't have that sort of aluminum sheet that we do, but they still work quite well. Another unique thing about SuperCDMS is in addition to having two targets, silicon and germanium, we have two types of detector. We have the ISIP and the high voltage. I talked a lot about the ISIP and how to do the particle discrimination, but I haven't talked about the high voltage. Basically, we gave up the background of discrimination capability in order to push the resolution even further. So the idea with the high voltage is that there's a 100 volts bias basically across the detector, and what that does is it amplifies the phonon signal. So you have your dark matter come in, it recoils, makes phonons. The voltage across makes electrons from the recoils, which makes more phonons, which makes more electrons, which makes more phonons, and you get an avalanche cascade. So the high voltage detectors really, they really improve our threshold, although they lose the ability for background discrimination. This is the total payload that Super CDMS is going to have. It basically consists of 4 towers, each with 6 detectors. You can see the sort of breakdown of silicon and germanium. There's going to be 12 ISIPs and 12 high voltage detectors. And then this is the Super CDMS experiment. So it's a lot to take in at first, so I'm going to kind of go through it piece by piece. The most important part is in the middle. That's what we call the snow box. The towers that has all these detectors on it, that's this red thing right here. It sits right there. The snow boxes are the different stages of the cryostat that we talked about earlier. The cryostat is off to the left right here. One of the things, the reason why it's so far away is to get rid of the vibrations. So these pulse tubes, our cryostat actually has 2 on it. You know, they cause a lot of vibrations. There's a lot of dirty radioactive parts in there that we don't want anywhere near our detector. So that's why it's kind of along this long stem, which we call the cryogenic stem, or the C stem. It goes into an insert right here, and it's surrounded by our shielding. We have different layers of shielding. So on the outside is water, just big water kind of bricks almost, that is going to be used to stop neutrons. On the inside we have some lead, some polyethylene, some plastic, and then there's also a mu metal shield. So one thing I didn't mention is that these detectors are very sensitive to magnetic fields. You'll see in a video in a few seconds a big crane that we operate on top. Even the motion of that crane is enough to cause our detectors problems. Now, the reason we have the stem on the right here, this is our E-tank. So when you have something that's so cold, millikelvin temperatures, you can't have warm electronics anywhere near it, otherwise it'll warm it up. So we have to cool down our electronics as well, and they come out of the E-tank on that side. The whole thing itself rests on a seismic platform that reduces the vibrations. Okay, and so now, this is our ultimate science goal. This plot is really a lot, so we're just going to go through it slowly. Basically, I only want you to focus on the solid lines, forget about the dashed lines. But what I want to illustrate is that how each detector and each detector type really carves out its own unique area of physics. So we'll start with the germanium high voltage. Here they have the best exposure, so they can get down sort of the deepest in this plot, and that's their benefit. The silicon high voltage, they have the best threshold, so that's the blue line. It kind of moves the best to the left here. The germanium ISIP only really dominates in this small area here, and the silicon ISIP doesn't have any area where it sort of leads in this hide-and-go sequence. But the ISIPs are still very important to have because they allow us to understand our backgrounds in situ, in the same site as our physics-leading high voltage. So these detectors are incredibly useful even though they don't reach the physics. The experiment has been under construction for a while, but it's really seen a lot of progress in the last 2 years. So this is the shielding I was talking about. You can see the mu metal layer in the crane that they're lifting up right there. There's the plastic inner shielding. There's the lead shielding. Each piece of lead had to be lifted by hand, so it was like kind of an assembly line of people, a bit old school style. And we're hoping that we can begin taking science data this year. This is a cool picture I like. So in 2022, this is all that there was of the Super CDMS project, just the size of the platform. The first time I visited SNOLAB in 2016, this hall was empty. It was actually just a bunch of tape on the ground. Actually, I think there's still some of the tape left right there. And now you can see just how much work has gone in 2024. So we already have the shielding. We have our big snow box right there. It's quite interesting. Yeah, so this is another video of something that was taken just last week. Remember we had those nested cans? So I want to show you kind of all the work that needs to go into it. Yeah, so they lift the can up, and they're going to put it in the big one right here. So you'll notice some people are in white. Because these cans are very close to the detector, I'm just going to pause it. Because these cans are very close to the detector, they take even more precautions in making sure that they don't contaminate it. Your sweat, your body oil, your hair, if it falls in, it would ruin it. So that's one of the things we do. Additionally, right now everybody's pretty much at lunch, except for some hard workers in the corner. But you notice they bag the cans, and they've actually filled them with nitrogen. And that nitrogen basically keeps out the air. In fact, even the air has radioactive contaminations. Particularly, you're worried about radon underground. So right now it's nitrogen purged, so you don't get any of the radon in. So everybody's at lunch right now. They come back, they put on the white suits. They're awful to wear. They're really restricting and not very sweaty. They're assembling the clamps, and then they've nested, you know, that can right there. And I think the video is going to end. Yeah. So that was a whole shift. That was 10 hours worth of work, you know, put one can in another. And to do it in a way that doesn't add any radioactive contamination. So it just goes to show you how long, you know, how many people were there. I think it was like 7 or 8. How many different people need to work to make this experiment possible. Okay, so that was kind of the super CDMS. I'm almost out of time, so I just want to go briefly through some other small areas of SNOLAB that has cryogenic components. So we have what we call the CUTE facility, the cryogenic underground testing facility. It's a more traditional cryostat, kind of like you've seen before, but this is open to anybody. You can come to us with a proposal, hey, I want to put this detector on CUTE, run it, that kind of thing, and then we do it. The benefits of CUTE is that we run in an ultra-low background, ultra-low vibration environment. So it's surrounded by a big water tank. We install everything in the CUTE clean room. This is actually a class 100, so 20 times better than SNOLAB itself in there. So everything in the cryostat is quite radio pure. And here's some of the things that CUTE has done. So one of the super CDMS towers was tested for about, I think it was maybe 8 months inside CUTE, just to kind of make sure it's performing well. And the answer is yes. These are some calibration lines. So you can see we're getting to quite low energy here. You know, that's on the easy scale. This is another type of calibration technique called CompuStat. So very promising things to see for the HV test. And it shows that these towers can actually work in an underground. There's kind of an expression at SNOLAB that it doesn't really work until you get it working underground. Because for some reason you can just go underground and it won't work. From last April to October, we had this HV-EV run. This is a R&D type detector. Basically what happens, it's a small silicon chip that we've instrumented, and its resolution can beat super CDMS's by quite a lot. It gets to the single EV scale, which is really impressive, and it ran for the first time. The reason to run it at CUTE was to investigate this low energy excess, which is kind of a problem all these cryogenic experiments are running into now. Yeah, here you can see the HV-EV detector. There's 2 of them right there. Like I said, it's about a gram scale, and this tower ran 6 of them. They basically sort of stacked them up like pancakes. And it was a really successful run for CUTE. The next thing that we want to do at CUTE, so this is actually going to happen from February to April, pretty much, is the first run of our superconducting qubits. So I'm not an expert in qubits, but the basic idea is you sort of have a superconductor, and the charge moves in one way or the other. This is your bit, so 0, 1. And then there's the quantum part where it can kind of be anywhere in between. The problem is that after a while, it goes into decoherence, so it's not moving the way you think it does. And one of the main theories behind that is it's due to the ionizing radiation, so the radiation that we experience on the surface. So the idea is to take these qubits, run them at SNOLAB deep underground in a low background environment, and see the effect on that decoherence time. So that's in collaboration with SNOLAB, University of Waterloo, and Chalmers University. Next week, they're actually starting the upgrade to the fridge. One of the big things you'll notice between a qubit-style fridge and the particle physics are these RF cabling right here. They're very rigid, straight cables that go through. That's how you can always tell what kind of fridge is for. If it has that, it's quantum related for sure. Yeah, so that takes me to the end of my talk. I hope you guys enjoyed it. What I really want to say, kind of drive home, is that these cryogenic tools are very useful to solving problems in particle physics. The idea is always the same, no matter what experiment you have. You need an absorber, some sort of sensor, and a fridge, of course, people. SNOLAB is 2 kilometers underground, and it's it should be a pretty cool place, not pretty cold place. Although it is actually quite cold. They keep it at a nice, I think it's like 20 degrees. And yeah, super CDMS is going to push the boundaries and be a world-leading experiment in sub-GeV dark matter, and hopefully be the one to find it. Thank you very much for your time, and I'll be happy to answer any questions.
Thank you very much. I know some people have to leave for class, so if you need to, please do feel free. But we certainly have time for questions for anybody who has time to remain.
A number of your graphs showed cross-sections for the interaction of dark matter with ordinary matter. What physics goes into estimating stuff that we don't know about?
Yeah, it's a great question, and yeah, something like this.
Yeah.
There is a lot of assumptions that go into this. They assume sort of a standard halo profile of dark matter, that sort of spherical halo I was talking about. They make a lot of assumptions about the nuclear form factors, the materials that are interacting. It's almost to the point where it's not a valid way to compare it, but we don't have any other way. A good example of this is earlier on. Here, I mentioned these two contours. So DAMA is an experiment that has claimed to see dark matter for the last 30 years. And they have a pretty compelling case. But you can see that they've been ruled out by all these other experiments. And DAMA's defense is that, okay, this plot isn't right. You can't make these assumptions. There's too many assumptions when you make these. You need to do a direct comparison to us. So it's a lot. If you ever watch a DAMA presentation, they have a whole slide which lists about 30 different things that could be of the assumptions that go into this. Yeah.
Thank you so much for your research. It looks amazing, and I am definitely going to leave that link for both undergrads. A really quick question, and perhaps from a different lens. A lot of my friends from other faculties, like political science, poli-sci, they ask, research like this requires a lot of funding, tens of millions of dollars. What can I say to them that will make me explain, oh, this is why this is important, or this is what it gave us in real world benefits?
Yeah, it's a great question. And the answer I always give is, if you look at the let's say three fundamental forces of physics, as our understanding grew of each of those forces, so too did the world change very dramatically. The electromagnetic force really led to the Industrial Revolution in the early 1800s, and understanding of that is kind of where we get to today. The weak force is incredible in medicine. All these imaging techniques, it all involves with that wouldn't be possible without that. The strong force, if you watch the Oppenheimer movie later, kind of led us into the nuclear age and beyond, potentially fusion, which could be an energy saver. So every time humanity has sort of discovered a new force, it's changed our direction. This dark matter, if it's particles, it's probably related to some new force. So it's reasonable to assume that by finding it, understanding it, it'll also lead to a radical change in how humans live. You can't say that for certain, but that's kind of the trajectory it's always been. The other thing with fundamental research like this, you have to think that the timescales are much longer. A great example is Einstein's general relativity. I found that in the early 1920s. We use that today in our cell phones to get exact position. No one would have said Einstein's research, it wasn't very applicable back then, but it is 100 years later. The first physicist to make a transistor, it was about this big. Now you have millions of transistors inside your phone. And so again, it's just those long time scales that always lead to benefits. So that's the answer I would give, is that yes, it's not a direct turnaround, you won't see it in a year, but usually, almost always, there is an excellent path to benefits to humanity.
I agree, thank you.
Yeah.
Quick question. So, as far as I understand, so you were saying you have 4 years of observations, but no detections, right? And you're pushing the limits down and down. So how do you know that your instrument is running, that you're observing, that you're, what kind of calibration procedures are you doing? So you can say, well, I actually didn't have enough. It's not like you can fire off, oh, here's the artificial, the dark matter particle,
yeah.
And this is how it's supposed to look like, right?
It's a great question. And calibration is very tricky. But basically, Super CDMS has two main calibration sources. It's almost, you can imagine a little pipe with a radioactive source that comes into the detector, and it's either a gamma or a neutron source, and then we use that to calibrate and see the performance of our detector. We typically have two calibration sources. The benefit of the gamma is it gets you clear energy lines. So it's a monoenergetic peak that we're like, okay, this is at this energy, so that kind of gives us an energy scale. The neutrons, I kind of mentioned it a little bit during the presentation, but neutrons will interact the same way we expect dark matter to. It's that same recoil. And so neutrons are actually great calibrators to make sure we're seeing these recoils and know our detector's working for a potential dark matter style event. Yeah, so that's the kind of the way we go about it. Yeah.
If I'm not mistaken, I think there's like a helium shortage going on right now. I have to imagine to keep your detector as cold as you do, you need to use a lot of helium.
Yes.
How has that shortage affected this project? Like, do you have some sort of recapturing system? Or?
So exactly, we do have a recapturing system. So I talked a bit about at the beginning these wet versus dry dilution fridges. Wet fridges burn off the helium, and without a recapturing system, we lose that. So luckily, we're running a dry dilution refrigerator, which means the helium we have initially will always stay there unless there's some accident where we open a valve and send it off into the atmosphere. But really, it's all self-contained in a system, in a cryogenic loop that is constantly going and providing our cooling. So yeah, in super CDMS, it's not an issue. I've worked on some experiments before where it was a wet fridge, and the helium shortage is rough. It's tough. You have to pay tens of thousands of dollars to get helium in, and then even then the lab's like, no, we need it for other applications. So it's not great. Yeah.
Is there an outcome of this experiment where it becomes no longer feasible to keep building more sensitive experiments, or you start to think maybe there's another path to look for dark matter?
So that's a great question. If we don't find it, there will always be people who say, okay, we need to push either in the sort of lower energy region or push more in the exposure region. There is an interesting area that's this dashed line right here. It's called the neutrino floor. And basically what it represents, it's the point where our detectors are so sensitive, they start seeing the neutrinos from the sun, from other sources. Right now we're above it, so we don't worry about that as a background. When we start to get below it, it becomes an additional background. And then the question is, well, does it really make sense to build and look there? Of course, dark matter theory doesn't care about the neutrino floor. Dark matter could be anywhere on this plot. It could be, I think, where did I show it? It could be anywhere in these mass ranges. So we really have to kind of pick the one that we think is the most motivated and look there, and then decide, is it justified to look even further? So, yeah.
Silly question. You're looking for direct evidence, which I think it means you're looking for particles that comes from space, right?
Yes.
So do you have like a preferred direction to point, or is just up?
Yeah, no, so that's a really good, and it just relates back to what I was just talking about. So, don't need that video yet. Yeah, so we are moving in our galactic circle, and the Earth is moving around the sun, which means it's getting a specific amount of dark matter flux that is directionally dependent. And people are talking about that these neutrinos, because the sun's always kind of in a specific place, they will have a different directional dependency. So the future experiments that people are talking about at this stage for this level does have some sort of need some sort of directional dependency in order to remove these neutrinos as a background. There are specific experiments that look for directional dependencies. It's very hard though to know which way the dark matter is coming from. It's actually one of the reasons the DAMA experiment is kind of stayed around so long, is because they don't actually measure individual hits, they measure a pattern over the course of years. So they look for a modulation in dark matter, and that's what they see. So yeah, directionality is going to be really important, I would say, in the next generation of dark matter experiments. The current one is just going to get us to this neutrino floor, and then in the next one, within 10 years, that's where it's going to matter. So yeah.
Just for clarification from my mind, right now this generation is looking up, right? Like the detector is pointed up and you cannot tell the direction.
So it's not quite like a telescope where we point it in a specific direction. It's more of like a little puck that is moving through a soup of dark matter. So the Earth is in a dark matter halo, and we're kind of just moving through it. So remember, I think I said it was 10 particles in a 2-liter bottle. That's always just kind of going through it. So it's more like running through the rain than it is pointing in a specific direction.
Okay.
Yeah.
Are your experiments sort of affected by, I I guess, the ways in which astronomers have found like where dark matter tends to exist and how we think it, exists in those areas. Like, for example, how there seems to be less dark matter in longer clusters. Like, do those kinds of things inform your experiments at all?
Yeah, so luckily in our galaxy, that's the only dark matter we can look at, right? Because it's what we're running into all the time. But there are bounds not shown on this plot that restrict how high we can look and how far to the right we look. And those bounds come from astrophysical observations. So yeah, it's really important. They you showed the cosmic microwave background. So that Lambda CDM model is a cosmological observation, and that kind of leads us into how we build these experiments and where to look. So yeah, they're definitely related.
Okay, I think we need to wrap things up. The questions are going to keep going, so if anybody wants to talk to Matt afterwards, he will be standing here. And I think he was going to say this, but yeah, I think he also has some swag.
Yeah,
If you're interested.
I have some SNOLAB sunglasses, and they have these pencils that like change color if you heat up, and some stickers and stuff. So please come and take as much as you want.
Okay, so let's thank our speaker again.